Hello, everyone. Welcome to the first episode of our 2026 monthly webcast series, Aftermarket Intelligence Unlocked. I'm Pechi, Head of Data and Analytics at Tavant. Great to have you all with us today. Each month on last Friday, we bring together industry experts for focused 30-minute conversation on what's changing, what's working, and what's next in manufacturing after the aftermarket space. Before we get started, just a couple of quick notes. This session is being recorded and we will share the playback afterward. We also encourage this is to be interactive, so please use the Q&A button to send your questions. We'll address as many as we can toward the end. Now, let's talk about the today's topic. We are diving into one of the most expensive and often overlooked challenges in field service, the dispatch decision. Traditionally, the dispatch has been reactive and rule-based, but today, with AI agents powered by reinforcement learning, organizations are starting to turn dispatch into a real competitive advantage. These systems learn continuously from work orders, IoT signals, and service history to reduce unnecessary truck rolls, improve first time fix rates, and protect SLA commitments at scale that simply isn't possible without traditional approaches. In this session, you'll also hear a practical way to think about ROI along with a clear path for moving from pilot to protection. I'm excited to be joined by Dr. Olav Laudy, Head of AI Consulting at Tavant. Olav brings over 18 years of experience helping enterprises translate advanced AI into real business outcomes. He also worked closely with both Fortune 500 companies and startups, leading AI first initiatives across machine learning, generative AI, and agent based systems. At Tavant, we are focused on helping organizations transform aftermarket operations through the data driven with AI powered solution, delivering better efficiencies, stronger service outcomes, and improved customer experience. With that, let's get started. Let me start with a simple observation. Most field service organizations today are still dispatching reactively. The focus is on optimizing next job, who is the closest, who's available, rather than optimizing for best overall business outcomes. And while they may seem efficient in a moment, it creates a ripple effect of inefficiencies. You start to see avoidable travel, technician not being fully utilized, repeat visits because the right skills or parts weren't aligned the first time, and ultimately missed the SLA and slower resolution times. All this adds up to an inconsistent and consumer experiences. But the real impact goes beyond just operation. At enterprise level, this drives higher cost to serve, puts pressure on contract profitability, increase service penalty exposure, and impacts customer retention and renewal potential. Now let's make it a bit more tangible. Imagine a field service team with a 20 technician, each with fully loaded annual cost of roughly 100K, with about 2 million field labor base. If you improve productivity just 5%, you are effectively unlocking around 100K worth of additional capacity without adding a additional new single technicians. If you reduce avoidable travel by 10%, you immediately lower the cost for work order. If you cut repeat visits by even 5%, you improve first time fix rates. So the takeaway is dispatch is one of those rare levers where even small improvements and decision quality can translate into a meaningful margin expansion and revenue protections. That's exactly where AI driven learning based approaches begin fundamentally changing the game. Hey, there is a poll and survey questions are currently running. Please feel free to choose those questions. Now let me connect this how we think about the solution. Tavant SLM acts as an intelligent layer across entire service lifecycle, spanning dispatch, routing, technician guidance, predictive insights, and real-time KPI visibility. Instead of operating as a disconnect decisions or static rules, it brings these elements together into a learning system at once. The objective is simple: the right technicians with the right context and the right moment. This means that system is not looking availability or proximity, but also factoring in skills, parts, job history, asset context, even predicted failure patterns. So the first decision is also a best decision. Now, I want Olav to start talking about what his thought process bringing in from rule-based versus optimization-based versus reinforcement-based learning, and how does it really helps in this to solve the technician problems. Olav, over to you.
Thank you, Petchy. Let me share my screen. Welcome, everyone. Now, I'll be showing you a demo, and I'll go in detail and of how this approach works. But you have seen the business context. Now, we solve this business context with something called reinforcement learning. That sounds complicated, and there's a lot of math behind it. I'm not going to take you through like the model and the technicalities, because that is not the purpose of this this call. But it is important to understand like how a model like that works. And while I show you the demo, I want to show you an example first that gets you an idea of how such reinforcement learning works. And I start with a simple game that you probably well know. It's called Space Invaders. And you see here that you have a little defender on the bottom, and it needs to shoot aliens, and the aliens shoot back, and it can hide behind some blocks. If it shoots its own blocks, then it dies. Now, how do you train a computer effectively how to play this game, or an AI agent, if you will? And that is a field that is called reinforcement learning. You provide pixel level data to this agent, and out of this basically like many different pixels, it has to kind of deduce, okay, what are the rules? And the rules need to be translated into actions. And those actions are simple. I go left, I go right, I stand still, or I shoot. And the way this works is that after you train this and train this, every time, maybe at the end of the day or at the end of the game, you say, well, your actions were not good, or your actions were good. And that translates in a slight update in behavior over time. Now, today, here you see that I have this agent not trained. If you look at the rocket, it doesn't really behave in a way that is logical. Now, I provide this 50,000 episodes of training data, and then I'll speed it up a little bit so you see what happens. And on the right side, here you see how well this agent scores. Now, there's 32 aliens to be killed, and that is my scoring. And you see that basically it mastered the game, because if I speed this up, and you see the agent very strategically move and shoot each and every agent without dying, or maybe dying once in the game, and basically showing that it completely masters the game. Now, this is what we want to apply, but then in the dispatch situation. This is the algorithm. And if we were to deploy that, what kind of data would you need is the next question. So you would take data as a priority level, customer ID, the resolution time, whether it fixed first time or not. And these are sometimes data that you have in systems, sometimes it's historical data. And based on that, you can create basically a training set for your reinforcement learning agent that with hindsight then can learn, okay, you know what? I made a decision here, but if I would have done this, I would have had a better outcome. And if you feed this type of data enough to your agent, after, I don't know, 50,000 episodes of computer time, right? It kind of understands the patterns in your business and makes decisions. So we have work order history, we have technical roster data, the skills that people have, the way the work schedules, their overtime, where they are based. We have included customer and asset data, right? Where are the customers located? What's the cost of downtime? What kind of contracts do you have? And then, of course, very important part inventory, right? You have a part catalog. Not all parts are available right away. Some parts deplete faster from inventory than others. They need to be transported, etc. Then you have geographic and time travel data. This is also not straightforward, right? Those are geographical locations, and it means that you have to dispatch a technician from a source location to a target location with a travel time. Now, I mean, if you have part of this data available, you can start to build this, but you get the full flavor of your reinforcement learning agent the more data you can provide. In our case, what I did, I simulated having this data available to show you a demo of how a dispatch agent actually works, and that it works better than rule-based or optimization research-based. And to that, I simulated this data, and I want to give you an idea of the realism of this data. First, there's some method that I'm assigning the first time fix rate dependent on a part, right? If a technician goes to a client, it's not always exactly clear what the problem is or which part you need to have with you in order to fix it. So that is a variable part. Then, of course, if you don't fix it in the first time, there's some kind of a cascade that needs to happen. And you need to assign a better priority of cases that were not fixed in the first time. There's more downtime cost assigned to things. You waste travel between the source and the target location. And then there's things like overtime that need to be taken into account. You need to ensure that if your specialist or if your SLA is breached, you take that into account because that is very costly. And then if you're simulating this data and try to create a realistic pattern that your reinforcement learning agent can learn from, obviously not all specialists have the same skills. And in fact, your best specialists are very scarce. Right? And that means, for example, that if Monday morning you get a call with a fairly routine issue, you're not going to send your most skilled technician there because a few hours later you might get a very highly specialized call, a problem getting in, and that is where you needed this technician for. Now, you kind of see that someone who manages those work orders like directly, they get a feeling for that. It's like, okay, but this is kind of easy. Let me send this person. They have the right skills for the right job. But it's not a formal process. And here we teach a reinforcement learning agent to learn those patterns exactly. Now, then in order to add realism to this simulation, we have parts depleting over the week. So not every part is always available. There's overtime, there's travel time variability, right? If you travel from A to B, that depends on the time of the day, and sometimes it takes longer than other times. And so we just create an environment for this agent where very clearly we ensure that the data we provide the agent is as realistic as possible. Well, what does that result in? We have three agents that I'm going to show. The first agent is a rule-based agent. And basically it says, look, a job comes in, sort the jobs by priority, the current jobs. Emergency is more than urgent, is more than standard, and so on. And then sort it by SLA deadline, and then sort it by customer tier. Right? And with that, you simply look at, for the first job, you look at all the available tech with matching skills, and you assign the tech on the job. I mean, that's not a dumb strategy. It's a simple heuristic, and you'll see it works quite well. But also, there's a lot of optimization to be gained. Well, the first level of optimization is when you apply optimization research tools. And effectively, what you're doing is you're translating your optimization of your scheduling problem into an optimization problem. You solve that mathematically. And that works quite well, and you have already a big advantage. However, this method has as disadvantage that it kind of can't foresee the future, right? Or anticipate the future. So it might simply assign a very expensive tech at a simpler problem, unless you're in your optimization kind of try to take care of that. And that is rather difficult. So while this method works, the reinforcement learning agent takes into account all those components, all those data elements that I showed earlier, and tries to really, given the situation, given the skills, given the type of parts available, given the travel time, try to make and learn to make the optimized decision. Now, how does that work in practice? I have created like 6 scenarios, and every time I run a scenario, it creates completely new data. So frankly, I don't know what the outcome is for today, right? If I start a new cascade. But I have on the left the rule-based heuristic method, then in the middle the optimization research tool optimizer, and on the right side the neural agent or the reinforcement learning agent. And they all get the same customer situation, and they will respond differently. So let me start that process, and I will speed it up 8 times, but you'll start to appear, you see there's travel or technicians being assigned to jobs, and they run over the course of a couple of days, and we see slowly that the outcomes start to come in. What is your SLA? Oh, here we see the complete outcome. Now, in the top here on the left, we see the reinforcement learning agent score versus the rule-based outcome. Well, the reinforcement learning agent did 14 jobs more, and it saved $1.5 million more on downtime. So that's for the customer. Well, that seems a very good score. It saved furthermore $1,000 on travel and $1,000 on overtime. Okay. Then if we look at the score of the optimizer versus the reinforcement learning agent, you also see that the agent does 2 jobs more, but it still is capable of saving the customer $1.1 million on downtime. Of course, this is simulated data, but I hope to have convinced you that the data that I generated was as realistic as possible. And now if we look through the complete scorecard or the comparison, you see that, for example, the cost per 100 jobs for the rule-based is $23 million, whereas the optimizer does $50 million and our reinforcement learning agent 11. That is a big change. And even with respect to the optimizer, you see that the reinforcement learning agent has done a great job, I would think. Then you see that it's also the miles per 100 jobs, right? It's quite a bit difference there, also with respect to the optimizer. And then the overtime is also much lower per 100 jobs, and the breaches the SLA breaches are a whole lot lower. Now, of course, whether you will achieve these scores on your data depends on what data you have and the specific circumstances. But I hope to have shown you an interesting way to solve this dispatch problem using an agentic method that truly learns from your data and makes the smartest decision, even compared to a mathematical optimizer. And with that, I want to hand it back to Patchy.
Thank you so much, Olav. I mean, it's very interesting to see how reinforcement learning optimizer is helping to save not only dollars, it improves productivity, it improves the whole lot of other scorecard that you're proposing. Great. So having said that, now I see a few questions on the chat window. So I wanted to see if you can, take an address of one of the most, compelling and critical questions that, normally we come across. And you touched upon briefly, but I'll, go through this. Most OEMs still run legacy work order system, never designed to feed AI dispatch layer. When you go into a 30 to 50 technician operation, what does data readiness look like on a day one? And what is the minimum viable signal across work orders, parts history, and IoT telemetry before an reinforcement agent that can outperform an experienced dispatcher? Can you take a stab at this?
I think the key is to have a correct recording of what tasks were performed by which technician and where they needed to travel. So effectively, I feel that you don't have to have a system that is completely adapted or open to reinforcement learning agents. It is much more, do you have the historic data available to learn from? And that can start truly with just I would say, an administrative trace of your past operations. That is the key to learn from.
Understood. Understood. Thank you. Audience, please post if you have any other questions on the chat window. At the same time, participate on the the poll as well. I have one more question that I wanted to see if you have a time to address this. In live dispatch, an agent simultaneously optimizes SLA urgency, technician skills match, parts availability, and travel cost, and these can directly conflict. When the highest priority job requires a specialist 4 hours away while generalist is nearby, how do you design the reward function for that trade-off? How does an agent weighing evolve simulated data to a real world outcome? Can you address this
Yeah.
question?
So you're introducing the concept of reward function. And I think it is important for the audience to understand that a reinforcement learning algorithm is indeed trained with respect to a reward function. And that means you will have to have your administrative trace that you learn from, but you will also have to specify a way to say, like, look, this was good behavior, or this was a case where the things ended up perfectly, and here it was less optimal. And so if you kind of quantify that, that is called a reward function. Now, in the creation of my simulation, I will tell that I had a lot of struggles in finding the right reward function, right? Because that is exactly something that depends on the business context, and you need to truly like experiment with that, right? So in the first time that I did this agent said like, oh, look, I can easily get a much better score. I just defer all the jobs, right? So the reinforcement learning agent thought it did a great job, but it didn't it didn't send any technicians. Then you also don't have any overtime, right? Because everybody stays home. And suddenly it means like, okay, I have to add a penalty for the fact if they start deferring jobs. I want them to act on that job. And so very carefully through looking through the results, I optimized my reward function such that I thought like this is the right way of looking at the dispatch problem. And I would assume that if you're going to do this in your organization, a similar evolution will take place. In the first criterion that you will have is like, well, we simply want the most jobs solved. right? But suddenly you realize that most solved jobs means that you also have high cost to solve those jobs. And you're like, well, I want high cost, but I want, oh, sorry, high solve rate, but I want lower cost. And you kind of like start to balance those things out. Luckily, the compute time for that is easy. So you specify exactly your reward function, and given that, you will provide an outcome. That outcome is clearly stated in terms of business KPIs, as I showed you. And if you can look through that and say, like, well, can we do better? Because I'm concerned with this. And that means you tune your reward function slightly such that it better aligns with your business objectives. So the better you're able to specify if your reward function aligns with your business goals, the easier it is to make a system like this work.
Thank you so much. Thank you, audience, for these wonderful questions. If you have any, such issues currently running at your organizations, how do we really qualify this? How do you really dispatch your technicians? We could certainly assess the situations. We have a framework, we have a product that can help you to assess your current problem. And we could look at exploring implementing, starting from reinforcement learning and, looking back to see if, rule-based plus the optimizer, the OR-based, optimizations and the reinforcement learning can help you to improve your current dispatch solution. Thank you all for having this as, and we look forward to connecting with you all again in the May month session. Wonderful day. Thank you guys.
Thank
Thank
you.
you.